Okay, so this is the expression then for the bright spots. And remember, if I'm looking at my screen here, um, my screen is here. I have a bright spot in the middle, and that's what gives this. I'm sorry, that's what gives this sort of. I show that with this plot right here. So this is a plot of the intensity. This is a bright spot right here. I have a dark spot, bright spot, dark spot. So this is the next bright spot. So the 0th order would be right here, and this would be the first order. That refers to these numbers. These are the order numbers. And then they go on, 2, 3, 4, and on. And we'll see later actually that this doesn't go on forever, that there is a stopping point where this stops. Now let's look at the dark spots. That's in between. So right here, for example. Now, the path length difference for two light rays coming here is 0 wavelengths. That's why you get complete constructive interference. Whereas over here, the path length difference between the two light rays is 1 wavelength. So whereas here, I get two light rays that come together like this, and I get complete constructive interference, up here at order number 1, I get two light rays that go like this, and then the second ray starts like that. So they're offset by 1 wavelength. But they still experience this constructive interference, but just not to the same degree as we do get for the 0th order. It's a little bit dimmer. Okay, now in between here, I'm going to be offset by half wavelength. So at the dark spot, I'm going to have my wave there, and then they're going to be offset by half wavelength. So my second ray will start after 1/2 wavelength, and it'll look like this. So that the peaks line up with the troughs, and the troughs line up with the peaks, and they just all go away. So that's destructive interference, where my path length difference is equal to 1/2 of a wavelength. So destructive interference occurs when the path difference in the two waves, it is 1/2 a wavelength. So since this is our path length difference, this is just going to be m plus 1/2 times lambda. All right, where m again is equal to 0, 1, 2, and on and on. So if I look at my, excuse me, if I look at my diffraction pattern, it'll look like this. I have my bright spot here, dark spot, bright spot, dark spot, and it's symmetrical. So here, this is going to be where my path length difference is equal to 0 wavelengths. That would be m equals 0. All right, so I plug in a 0 here, and my path length difference would be 0 plus 1/2 a wavelength. This would be the part where it's 1.5 wavelengths. So I'd plug in a 1 here for m, and it's going to be 1.5 wavelengths is my path length difference. Out here is going to be 2.5. All right, so that would be where this number would be 2 plus 1/2 times lambda. That gives the requirement for the path length difference to give me destructive interference. Now further, I can find the distance between the central maximum and the brighter dark spot by this. That's y equals L tan theta. Let me show you where this comes about. So let's say I have a screen here. This is where my slit is right here. I have this double slit, and I can draw my axis. This distance is L, and this is going to go up to the screen where I have my bright or my dark spot. It doesn't really matter what it is. And this angle is the angle theta. This is the same angle theta that I'm calculating up here. So that's the same angle theta. What I want to know is what is the distance from the central maximum to whatever is up here, the first bright spot, the first dark spot, the third dark spot, whatever it may be. I'm going to call this y. Well, look, I have a nice little triangle here. There's my hypotenuse, there's the two legs. I know that tan of theta, let's see, what is it? SOHCAHTOA, right? So it's opposite over adjacent. So the tan of theta is y over L. So y is equal to L tan theta. That's this distance. So if I have, for example, let's say that this is my bright spot, and I want to know the distance from the central maximum to the first bright spot. That would be my value y. in practice in the lab, you'll be measuring Y, and then you'll use that to either measure the width between the slits, or more importantly, to find the wavelength of the light, because the wavelength of light is actually fairly difficult to measure, but measuring the distance between these spots is actually quite simple. Alright, so that's double slit diffraction. I have a video I want you to watch. It's kind of a long video. It's about 8 minutes, but it's very good at describing what is double slit diffraction and why it's important, and the effects of it, like the experiment that Thomas Young originally did. So you can watch that here. And then here are a couple of quick test questions that you can try on your own. I'll have the solution up for these on the online quiz page. And next time we will do single slit diffraction. You can watch the Dr. Quantum video. It's kind of fun, so I'll just include it here. If you want to watch it, that's fine, but you don't have to.